One of the most important things that we're going to study in relation to vector fields is that of the curl. Now, to help you visualize the curl, just imagine a stream of water. And the stream is flowing along and you drop a leaf into the water. Now, imagine that when you drop the leaf into the water, it starts to spin around like on an axis. Like if it was, like at the center point, it kind of spins around that point. Well, we would say, okay, that's evidence of curl. That rotation around a little an axis there is evidence of curl. Now, if it didn't rotate at all, and it just flowed along with the water, along, with the stream, we would say that's evidence that there's no curl. Now, so this will help you to have kind of an idea about what we're talking about. It involves rotation. Now here I've put partial graphs of 4 vector fields, F, G, H, and K. And think of these as vector fields that kind of describe, I don't know, the velocity in the water. Okay, on the top of the water. Now, let's look at this first one. Imagine if I drop this leaf in here, in this water. What would happen to the leaf? Well, you'll notice that for the smaller values for x, the magnitude of the velocity is smaller than for the higher values for x. So what happens is, in this case, these vectors over here have a higher velocity, or have the speed is greater than the vectors over here. So what happens is this side of the leaf gets pushed upon more strongly than this side. And what happens is there starts to be a rotation, right? There starts to be a rotation around in the counterclockwise direction. Now we're going to say when that happens, we talk about the curl of the vector field being greater than 0. In other words, we have a positive curl. Now for this G vector field over here, it's different. Now if we drop a leaf in this water, it's much more strongly in this way. So because these vectors have a higher magnitude, so our vector is rotated in the clockwise direction. And in that case, we say that the curl of G is less than 0. But this helps you to understand what we talk about when we talk about curl. Now let's skip over here to this K vector field. Here, all the vectors are the same direction, same magnitude. So we would expect there to be no curl here. So we would expect in this case that there is no curl. Irrotational. There's no rotation whatsoever. Okay, now let's look at the H. And let's suppose that we have a point in here. And we want to think about the rotation on this in this situation. Let's say this is the leaf. Now notice we have vectors pushing up this direction, and down and to the right. So it's pretty clear here in this situation, you can clearly see that we would have a counterclockwise rotation. Okay, spinning this leaf around. So here we would have a situation where we have a positive curl. Now, what I want to do is kind of explore that particular type of graph. And I've got this vector field that I'm calling f of xy, and it's just the general vector field, mi plus nj. And let's suppose that I've got this point in here, and I've got vectors going to the right, up, to the left, and down. So in other words, these are 4 vectors that I've graphed around that point. Now, one of the things I want to take note of is, let's just think about this vector right here. Into the vector field, we put a point. Let's say x1, y1. And when we put that point in, that was our initial point in drawing our vector, and then we had a terminal point over here. Well, obviously, if we went from here to the right, that means that the m component is definitely greater than 0. Definitely. So we have m is greater than 0 for that vector right there, because we went to the right. the x component of this vector field increased. Now the y didn't, it stayed put, but the x did. Now let's explore that a little bit over here. I've kind of magnified for this picture right here. And here's the vector that we're looking at, this one right here. Now notice that as y increases, in other words, what I want to do is say, well, what's happening to m as y increases? Well, y has increased right here for this first yellow vector. And what's happened to m? It's gotten a little bit shorter, right? For this vector, we went over 2 units. This vector doesn't go over quite 2 units. See, that would be 2 units. So the m is getting smaller. We go up again to this vector, and notice m is smaller still. Until here, m is completely 0. When we put in our x and y into the vector field, we get an m of 0. Now the next step would be this vector, and notice this vector is actually pulling a little to the left, and now m is less than 0. Okay, so we started here with m greater than 0, and we end up here with m less than 0. Now we're looking at how m changes with respect to y. As y gets larger and larger, what happens to m? Well, another way to say that is the partial of m with respect to y. And we were positive, and now we're negative. This tells us that we have a decreasing. The partial decreasing situation. The partial of m with respect to y is less than 0. As y increases, m decreases. Now, I want to do the same thing for the n component. Because if you notice here, n is less than 0. Definitely. And, you know, we can make the same argument because we put in the xy and we go down. The y decreases. It starts here and it ends up here. That's definitely decreasing. Now, as we move to the right, something happens, though. We get over here where n is greater than 0. So it looks like, now remember, we're saying what does n do as x increases, as x changes? In other words, we've got the partial of n with respect to x. And that's definitely greater than 0. So it's increasing. Okay, now remember, here's what we want to happen. When the curl is counterclockwise, like this situation here, when we have a counterclockwise rotation, we want our curl to be positive. That's definitely what we want. So let's see how we could come up with a formula involving these partials that would give us that. Okay, well, let's take the positive here. Let's take the partial of n with respect to x. Okay, that's positive. And let's subtract from that the partial of m with respect to y. Now, if we do that, and the partial of m with respect to y is negative, this is going to give us a positive curl. Now, if on the, so this is the formula that we want to calculate curl if we just have R2, if we're just in R2. Now, you can play around with this and see, okay, well, if you have a clockwise rotation and you go through this same routine that I did here, what you're going to get is you're going to get a negative curl using this formula right here. So we say that the curl of this vector field is given by this. And this is how we can calculate the curl with in R2. Now what we want to look at is, well, what about R3? Now I'm not going to go into as much detail for R3, but here's what we're going to do. To calculate the curl for R3, we're going to use del. And remember, del is this operator, this differential operator. Okay? And what we're going to do is we're going to apply that to a vector field with cross product. Now, we're using the cross product as a way to remember the formula for calculating curl. But here's what's going to happen. We're going to take del cross F, and here's the way that's going to look. That's going to be partial x, partial y, partial z, z. And we're crossing that with m, n, and let's say p. Okay. There's our vector field. And here's actually how we're going to proceed. We'll do this. We'll say, okay, this is equal to I, j, k, and we have our partials. Now remember, this is the operator, and we're applying these to this vector valued, this vector field. So we have m, n, and p. Okay. And we would actually work this out the same way as we always do. This is going to be I, and then we say partial of p with respect to y, minus partial of n with respect to z. Okay, that's the first part. So we just did this minus this. Now I'm going to proceed just as we always do, partial p with respect to x minus partial m with respect to z. And then finally, the last one, partial n with respect to x minus partial m with respect to y. And that's how we're going to define curl in R3. Okay, now let's look at an example. Let's suppose that I've got a vector field. Let's suppose we've got, let's say, xy squared z to the fourth, and then we've got 2x squared y plus z, and then finally y cubed z squared. So let's so what I want to do is I want to find the curl. So here I go. Remember, we're going to use a cross product. So this is going to be I, j, and k. And now I do my differential operator. So this is how we would set it up start to finish. And the reason I'm doing this example is to be sure we know how to use this differential operator here. So we have xy squared z to the fourth, 2x squared y plus z, and y cubed z squared. Okay, now. Okay, so here we go. First of all, I'm going to take the partial with respect to y of these two terms right here. So this is going to be I, partial of, with respect to y, that's going to be 3y squared z squared, minus, then I do the partial with respect to z, and I guess that's just going to be 1. Okay, that's easy. And then j, so now, and I'm just going through working this exactly the way we always do in finding cross products. So now I block out the middle column, and I'm going to take the partial with respect to x. Well, that's 0. Okay, so I did this one and this one, partial with respect to x, and then partial with respect to z. Well, that's going to be 4xy squared z cubed. And then finally, I'm at the last one where I'm going to take the partial with respect to x. So this is going to be 4xy. Okay, so I did that one. And then the partial with respect to y, that's going to be 2xyz to the fourth. And that is the curl. And what this curl does, it provides information about rotational aspects of motion. So, and as we go along, we'll learn more about this curl. But right now, this is the, the basics.